The title of this talk is Give Rust a Chance, and this is sort of less of a how-to talk and more of a why-to talk. So what I hope to do is convince you that it's worth trying to implement something in Rust. And the person that I kind of have in mind when thinking about this is somebody who has an idea for a library, so a working data scientist or data engineer who wants to write a library that's going to get used by your peers. And someone who's coming mostly from a Python programming background, who sort of is for the first time grappling with some performance issues and has to think to themselves, great, I've written this great time series analysis library or this geodata analysis library, but now I actually need to make it work performantly so that people will actually use it. So that's sort of the idea to have in mind. So briefly about me, I'm Slater. I'm a partner at Bain Capital Ventures, where I invest in early stage infrastructure software. I come mostly from a data science background, so I've sort of led data teams at a few different places, and then I'm from a data IC background before that. So a lot of what I focus on at Bain is tools for data teams, something that's going to get used by the working data scientist or data engineer. And I first started thinking about Rust as a language for data through our investment in Polars. So as many of you know, Polars is a lightning-fast data frame library that's written in Rust, but that most people access through its Python API. And it just started me thinking about this general pattern of using Rust for sort of the lower level data processing, but exposing a Python API to users. So let me start with what I sort of perceive as the problem here. So the problem is that Python won the language wars and became the de facto language for data teams. So on one hand, if you want to build something for data teams, you have to expose a Python API. But on the other hand, Python itself, it's an interpreted language, and it's very slow. So if you are somebody who's building a library that you'd like other data scientists or data engineers to use, you sort of find yourself in this bind, where on one hand, you probably come mostly from Python programming background. Your users expect to use your library in that way, but you can't actually write sort of the under the hood data processing in pure Python. You have to do something else. So this isn't a new problem, right? Python's been around for a long time, and people have obviously written high-performance libraries for data teams. So what have been the historical solutions? And I'll sort of pitch you on why I don't like either of those solutions. So one solution is you could just learn C, right? How hard could it be? It worked for NumPy. It can work for us. Certainly one option is we could go buy a copy of Kernighan and Ritchie, learn enough C to be dangerous, and actually try to implement whatever we want in that low-level language, right? So it's certainly doable. I don't want to make it sound like it's not. But the reasons why I sort of find this a dissatisfying solution is that if you're coming mostly from a Python programming background, a language like C is going to seem extremely low-level at first. You're going to have to worry about explicit memory management. There's a lot of sort of pointer bookkeeping that you have to worry about. And it's not so much that you have to do those things, like any low-level language is going to force you to think about things like that more than you would have in Python. The problem is that it's very easy to make subtle mistakes in C, and things that you're not necessarily going to catch early on. So if you're sort of just getting started and trying to write C code, as I imagine certainly I would be if I was in this situation of wanting to write my first high-performance library, it's quite hard to get started. And it's sort of just not a very good part-time language. Like, we're not trying to become systems programmers here. We just want to build something that can be used by other data scientists and data engineers. And I don't think C is very good for that, despite some of its other advantages. But that's certainly a solution, right? We could learn C. I think the other solution is you could hope that somebody else learned C, right? We could sort of try to stand on top of our predecessors. We could sort of try to figure out a way of taking all the things that we want to do and express them in calls to standard libraries like numpy, scipy, et cetera. And I would say this is probably the default way that people get started, and it's a pretty reasonable thing to do. But I kind of am dissatisfied with this solution too. I think the problem here is sort of twofold. There's like an object level problem, and there's a more subtle problem too. And the object level problem is that it's just hard to vectorize everything. Like, I think procedurally in terms of for loops. I don't necessarily think about how every single thing that I want to do can map onto some existing API. So it can be quite hard to wrestle everything into calls to libraries that exist already. And I think you actually have to be quite careful too. You need to make sure that you don't accidentally use some pure Python somewhere, no Lambda functions in the applies, like that kind of thing. And you sort of generally have to be very careful if you go this route, if you actually want to preserve performance. So that's sort of the object level reason. I think there's sort of a deeper reason here too, which is that I think it's just kind of conceptually limiting to have these black boxes that we treat as like the primitives for doing anything high performance. So it's great that we can use some vectorized method once you learn how to use it, but it sort of creates this feeling of that's a black box that's written by somebody else. I'm never going to peek into the internals and see this sort of like inscrutable under the hood code. It just doesn't feel like something that's very hackable or very open. It's sort of like a system that you can't peek into and edit to do other things you might want to. But anyway, I think these have been sort of the two historical solutions, right? It's either you stand on top of existing libraries or you sort of learn some C. But this talk isn't about C, this is about Rust. And I want to pitch you on why Rust is the one true solution to our problems. And I'm going to skip over some other things as well. So you could go through Java and Jython. There's these compilers like numpy that you could use too. They're all great and have their place. But really the point that I want to get across is that Rust is worth trying in situations like this. So why is Rust the solution? There's a lot of great things about the Rust language. I'm only going to talk about one of them, which is that you can write bad Rust code, and it's fine. You can actually get pretty far writing bad Rust code. And this is important because like when you start out writing a low-level language, you're going to write some bad code. And the question is just, how much does that hamper you? Can you get done what you want to get done, or are you going to spend the next 10 weeks like chasing down sig faults or something? And so I think the advantage that Rust has is that, especially when you're first getting started, you're going to be more productive in it, and you sort of will make fewer mistakes and get further. So maybe as just one example here, here's two matrix multiplication implementations, one in C on the left and Rust on the right. I have no idea if these are particularly good implementations. They're probably not, but they are the sort of thing that you would write if you were just trying to do this for the first time, right? Like how to multiply matrices. Why don't we just write the code that does that? And the point that I want to make here is that if you look at the Rust side, it does look somewhat low level, but it's sort of basically intelligible. And you'll have to take it as an article of faith that as you're writing this and sort of trying to get it to work, most of the problems are things that you're going to find early on. Like the compiler will tell you when you're making mistakes, and you're going to discover these things relatively quickly. The iterative feedback loop will be short. Meanwhile, over on the C side, looks reasonable, maybe a little bit more low level because we have to explicitly allocate the memory. But it also seems like the kind of thing that you would write if you were first trying to do it for the first time. But there's actually like a subtle bug in this C code. Maybe I should say there's at least one bug. There's one that's there on purpose. There's probably more that I put there by accident. But it's not a compile time bug. Maybe I'll sort of, if someone wants to come up to me afterwards and point it out, you'll get some type of points. But the point is that you could write this and think that it was working and sort of not notice some of the subtler mistakes that you're making. And that's really the advantage that Rust has over C in this situation. Because again, we're not trying to become low-level systems programmers professionally. We're just trying to implement whatever algorithms we need so that we can get back to thinking about geodata or time series analysis or whatever we wanted to do in the first place. So maybe the high-level way that I would describe this is that Rust just stops you from doing a lot of bad things. Rust is memory safe by default. You don't have to think about whether you're pointing towards valid memory all the time. You don't have to sort of think about garbage collection. Rust has nice concurrency primitives. You don't have to worry so much about race conditions. And Rust has a very strict compiler. Like the compiler will complain to you a lot, everything that you do. And these are all actually good things. These are sort of safety features that you want, especially when you're first getting started, because they prevent you from making time-costly mistakes. So my dad was a general contractor. I sort of like this power tools analogy where up on the left here on the top, we have two tools. So on the top, we have a angle grinder, and on the bottom, we have a table saw. These are both powerful tools. You can do a lot with them. But I would sort of argue that the angle grinder has a reputation for being inherently unsafe and sort of hard to make safe. The reason is that you sort of have this small saw blade that's spinning at the end of a stick, and it's very easy if you sort of nick it the wrong way to have the saw move out of control. It's sort of a tool that's inherently hard to make safe. And on the other hand, we have this table saw, and in a modern setting, we have all these things that we've added to it over time that make it much safer. So there's this riving knife on the other side of the saw blade that sort of prevents you from accidentally turning the board the wrong way so that it kicks back at you. We have this nice yellow push block here so you can keep your fingers nice and far away from the actual spinning blade. And the point is that by adding these safety features, you make it much easier to get started. You don't have to worry so much about doing something dangerous by accident. So obviously it's nice to have code that's safe. It's nice to have things that are going to be more correct on average. But maybe the broader point that I want to make is this is actually freeing in a way. So with Rust, you'll make fewer mistakes because the language just prevents you from making them. Those mistakes that you do make will be easier to find, so they're sort of less costly for you in that sense. And because of these things, if you sort of just lean on the safety features a bit, you'll be more productive during that early phase when you're just trying to write an implementation that will let you move back to thinking about the problems that data scientists and data engineers face day to day. Sort of in the early bad code phase, you'll actually get the productivity gains you want. You will write code that runs faster, and you'll sort of spend much less time debugging it. This is freeing in the sense that when you don't have to worry about safety or accidentally shooting yourself in the foot, you can just go much faster and try more things. You don't have to spend so much of your time worrying about accidentally doing something in C that you're going to regret later. So maybe kind of the last thought that I'll leave on is that after we made our Polars investment, I went out and talked to a lot of the sort of modern group of Rust implemented companies in the Python ecosystem. And it was interesting to me that many of the authors of those libraries were not Rust programmers before, and many of them were not systems programmers before, but they sort of felt that they were able to pick up what they needed to know as they went along and built these very successful libraries. So my closing message is that it is much easier to do than you think, and if you have a great idea for a library that's going to get used by other data scientists and data engineers, you should try it. And I think you'll be pleasantly surprised with how much you can do. Thank you.